pleasure to be here. Thank you all for being here. So, title is, as you see, Atiyah-Bott localization from Witt-sheaf cohomology. So, what's the idea? So, in enumerative geometry, you have integer valued invariants, counting things, and the overall idea is to lift this to you have a problem over, say, some non-algebraically closed field like the real numbers. You want to lift your answer to a element in the Grothendieck-Witt ring of non-degenerate quadratic forms or virtual, so sums, plus and minuses of such things, Grothendieck-Witt ring, and you recover the integer value by taking the rank. Now, if you take k to be reals, you have another integer, signature, and this often tells you a lot about what happens to the problem, to the real solution of your problem. About that, and except to say that there's a quotient of the Grothendieck-Witt ring, the Witt ring. Take the Grothendieck-Witt ring modulo the hyperbolic form, xy goes to x squared minus y squared, and yeah, in this case, this is almost the same thing. Here, the difference is essentially you have a rank map to B mod 2, and other than that, it's the same thing. So all the information, your interesting information that you want to get in the Grothendieck-Witt ring, you can get in the Witt ring. And so that's the idea. So you can promote this to a cohomology theory by taking some smooth variety X and sending it to the cohomology, say Zariski and his neighbor cohomology in the sheaf of Witt rings, where that's the obvious thing. You take the Witt rings of the sheaf of functions. And sometimes it's actually, this becomes a cohomology theory. When you want to take the push forwards, you have to, it's like real topology, real manifolds. You have to include the information of an orientation sheaf sometimes to take push forwards. So you can twist the Witt-sheaf by a line bundle, essentially by looking at a set of quadratic forms valued in your field, or you look at quadratic forms valued in the one-dimensional vector space of the fiber of the line bundle. So that's a twisted version. And that's your cohomology theory. And if you have some vector bundle on X, you get some Euler class of the vector bundle in the, this has rank R in the R cohomology, twisted by the inverse of the determinant. And if the vector bundle has an orientation, which means that you have an isomorphism of the determinant vector bundle with some square of a line bundle, tensor the dualizing sheaf on X over K, the square doesn't change quadratic forms. You can take the square root of the square, and that says this thing becomes isomorphic to HR X, the Witt-sheaf of the maybe inverse here. And now if R happens to equal the dimension of X, then there's a push forward map. That's the orientation is what you need to take push forwards to the H0, which is, so H0 on spec K. W, you lose the twist, and this is just W with K. In other words, you get in here this element, let's just call it the degree, the W degree of this Euler class, we're going to decorate this, of V. And this is the thing which, when you can also do this in the Grothendieck-Witt ring, but this thing corresponds to the usual degree of the top term class in the, if you're working in cohomology or Chauvet. So that's a little overview of what this whole theory is about. And now I'm going to tell you a little bit about the particular story here. Okay, so Atiyah-Bott localization takes place in equivariant cohomology. Some group, the classical case, a torus group. And so I want to say a little bit about equivariant cohomology in sort of the algebraic setting. So how do you do this? You use an algebraic Borel construction, which was, I think, first used by Pitaro to define the Chow groups of algebraic groups, and then was refined a bit by Eddy and Graham. And then in motivic theory, that plays a role in Borel-Vojevodsky motivic theory. So what is this? Let me just take, we'll fix from group G, think of like SLN or torus group or whatever, sitting inside of GLN. We fix that. And it'll turn out all the choices we make don't matter. So just to remind you. And now GLN acts as usual on the space, let's say U and M. This is inside of N by M matrices. Viewed as a scheme. This is a scheme. This is just affine M space of dimension Nm. And inside of here, this is just the matrices maximal rank. Well, let's say of rank n. So if m is less than n, this thing is empty. And GLN acts on this thing. And of course, when you take the quotient, this is just the Grassmannian of, what is it, of n planes in M space. Okay. But instead of taking the quotient by GLN, you can take the quotient by G. Right? And these things fit together, of course. You can, if you increase M, you have a projection map from the matrices. In other words, you think you just project on the first M columns, right? From the M plus 1, you get rid of the M plus first column, project on the Mth column. No. You just increase, sorry. You take U and M. So you get these maps. And so if you have some reasonable cohomology theory, so cohomology is given by some spectrum here, but don't worry about this. It gives you, for any reasonable smooth Y, you have bi-graded cohomology groups. And for our example, we're going to take this to be the cohomology Y with coefficients in Witt-sheaf, but there are other examples. You could also take motivic cohomology, also take the H Y, like that, motivic cohomology. There are lots of examples. Think of it just as a placeholder. And then you can take the inverse limit for M is D, the gadgets M. And this you think of as the classifying space. You form a so-called homotopy module out of the Milnor K-sheaves. And that has an Einberg clay spectrum, which represents the cohomology of the Milnor K-sheaves. And then you have this map eta. When you invert eta, it transforms this graded collection of Milnor K-sheaves into the Witt-sheaf. And so if you take the eta inverted Milnor-Witt Heilenberg-MacLean gadget, that gives you this. More generally, if you have your G acting on the left on some space X, you can do the same thing. You can take X cross these UNMs on G. You take the E, A, B of these things, limit, and you find this to be the equivariant cohomology of X. Okay, so we're going to make the following hypothesis. True is that all these limits are all these limits potentially constant. Well, if we fix A and B, where it stops might depend on the choice of A and B, but when we fix the A and B, then they remain constant. And this is true, this is satisfied. Our examples are you can also take things like Witt-sheafs, things like this. This gives you back, when we take the stars equal to each other, this gives you back the Chow groups, which gives you back Totaro's the gray entity definition. All right, so where am I? That's equivariant cohomology. Any questions? Maybe, yeah. And then if we have V on X a G bundle, then we have the various Euler classes of V. We can do the same thing. We get a G bundle. We get a bundle on space here. And these guys in M give rise to this class here, and I have my hypothesis. This gives me this class E, G, B in, well, it would be in to the indexing goes like this of X with a twist by the determinant. This is assuming E is what's called an SL-oriented theory, which is in all of these cases. So I should say 4 of these cases. So for example, if we take the bit theory, get my equivariant, maybe I should call this something, you know what, I'm gonna not dress this up.
We have
okay, so that's the Euler class. If you have a theory like the Chow groups or motivic cohomology, you also have all the other term classes. You don't have them in things like this. So I make some computations of at least the coefficient rings for a theory that we're interested in. So the familiar one is when you take the group to be a torus, and you take, let's say, the Chow ring or motivic cohomology or just singular cohomology, that works out. The singular cohomology case is the one considered by Atiyah-Bott. But I'll phrase it in terms of the motivic cohomology or the Chow ring. Okay, so some
computations.
This is the coefficient ring. So let's take E, the Chow groups. Okay, and let's take G to be a torus. And then if we take the T-equivariant Chow groups, T-equivariant Chow groups of B, well, the Chow groups of BT, which is the same as the equivariant Chow groups of K, get the notation right. This is just equal to Z, which is the Chow groups of K, join some elements P1. So what are these T's? Ti is just equal to the first term class of the bundle Li, where a bundle, you think of this as a bundle on the dt gotten by the represent the character. You have this projection character here. Then projection. This Li is the line bundle on dt corresponding to this I projection. Okay. Now, if you take E to be, now if you take, here's the funny thing. If you take this to be the Witt-sheaf, which is the thing we're interested in, then you get this H star dt coefficients in the bit rate. This is just equal to W of K. So, K. In other words, you don't get anything new. All these the term classes are all you have, and these all vanish. Term classes, so the funny thing is, the term class is the line bundle. So the first term class is its Euler class. The Euler class of an odd rank bundle in bit theory is 0. The way it goes. So this is completely useless for us. Don't even want to think about it. So now the next thing, now we want something we do want to think about. So the idea here is that you take n equals 1, you have GM. But GM is complex points, it's just a circle. So you want something like a circle group. So but you want the real points to be a circle group. So SL2. So that's what you do. So now you take G SL2, and lo and behold, if you take the SL2, well, you take H star B SL2 with coefficients in the Witt-sheaf. This is, or maybe you might take this to the n. This is E1. What's EI? EI is equal to the Euler class of the Fi, where Fi is the bundle corresponds to the canonical representation SL to the n, so by the I projection L2 sitting inside of Geo. So it's a rank 2 bundle corresponding to the canonical embedding of the I factor of SL2 in Geo. Okay. So that's a theorem of non-equivariance. Okay, so that suggests that for the purpose of the Witt-sheaves, see, and if you take the real points of SL2 to the end, it's an n-dimensional real torus. So that's exactly what I'm saying. So it suggests that we want to do equivariant theory and make computations like the classification of the torus, we should look at SL2. Unfortunately, there's a fly in the ointment, which I'll discuss a little later, but SL2 is not the best thing to look at. Something better, also not perfect, is you take n, which is the normalizer of the torus inside of SL2. So SL2 contains GM, which is just the diagonal matrices. Right there. And this contains a slightly larger group. This is the group generated by GM together with this one extra element sigma, which normalizes the torus. So it's no longer a connected group. And you could also take n to some power, but let's just, and this thing here is almost, in the case n equals 1, you just have this one class, so I'll call that E. Of course, we have this map, of course, B n E SL2, right? Because you're just taking a quotient by a smaller group, so you have a 2 to 1. So you have a cover, and it turns out this thing has the following presentation. You have this Euler class. This E is the pullback of the Euler class coming from here, and then you have one extra element Q, which is in degree 0, satisfying the following relation: 1 plus Q times E is 0. It only shows up in degree 0. This is sort of a global quadratic formula. let's do the classical case. Okay, so the idea is that after you invert something, so you take some in this case scheme X with a torus action, and its equivariant cohomology is that if I pull back from the point, it's a module over the equivariant cohomology of the point, which is just the cohomology of BT, and we know that's a polynomial ring. And each of the variables corresponds to a character. And in fact, if you take any character, you just get a linear combination of those variables, right? With Z linear combination. So the idea is you can reduce the T equivariant cohomology of some T scheme X to just the fixed points, the cohomology of the fixed points, if you invert a suitable product, finite product of these characters. So why would that be the case? Let me just quickly explain that. So the theorem is there exists a product, let's call it C Li is non-zero. I'll stick with the child. Such that if you take the inclusion here on the X, morphism of the C star X. Okay, and also this thing, since now this has a trivial action, this is just the usual Chow ring X answered with the Chow ring E. Okay. So that's the first thing. And so why is this true? The rough idea is you can stratify X as a disjoint union of Xi's, these are locally closed subschemes, that's locally closed stratification, and each Xi, we sort of use Hilbert theorem 90 here, that would be some can read it as T mod HI plus YI. You expect the YI's to be smooth, and the HI's are just some subgroup of TI. So of course, if HI is T, then this is just the fixed locus, right? The group is inactive. So, and now the point is, if you take T mod HI, if the dimension of this thing is bigger than or equal to 1, then there exists some projective homomorphism with GM. Right? The HI might not be, if it's we're connected, then this is just, lattice theory for the integers, right? If it's not connected, you just raise it to some power to make it connected, and then you use the same thing. And then you have this surjection here. And so this is just a character, let's call this chi-I. And the point is that if you take now, if you take the, so now that gives you an action of T on this GM, and if you take the T equivariant cohomology here of this GM, I'll call it GM II, and this chi corresponds to a line bundle L chi-I, and if you take in here, you have this, and you have this pullback map. Here you have this C1 of this L chi-I. This goes to 0 in here. With an easy calculation. You've trivialized the line bundle by pulling up to the space of the character in some sense. Okay, so what does this say? This is a finite gadget here. So you let C the product C1 that is L chi I. Remember, this thing is just some. This is just some linear form. A linear form in the variables, and you take the product of these things. That tell you that if you invert this guy here, well, you've inverted 0 in here, but that means you've inverted 0 in the cohomology here, right? You invert this, then the equivariant Chow groups of these xi's, sorry, 0 as long as the dimension of hi is so by inverting C, you kill all the factors corresponding to non-trivial orbits, and all that's left are the fixed points. That's the idea of the proof. Okay, now there's the second component to this is, so once you have this isomorphism, and now say you have some equivariant, some T vector bundle, and you want to compute its Chern classes. Well, it comes from something on the fixed points. What does it come from? That's the Bott residue formula. Okay, so now the second part is you have the Bott residue formula. So suppose you have some T vector bundle on your X, and then you want to compute sort of the T equivariant Chern classes in V. This will live in H in tau I. So how do you do this? Well, the thing is, we know that this thing is the same. Oh, I'm sorry. This is the same as Chow. Well, let's assume, which is going to be always the case, just to make life easier. Let's assume that this thing is a finite set of points, and that let's let T equal dimension. We had this push forward map, so of course this comes from after inverting C. This comes from Chow minus. Of course, it's going to be 0 of the xi's. Right? So you're only going to get the top Chern class by this. So you can assume that, let's say, J and P. Okay. And now what's the, so here's my I lower star. Bott residue formula says that this E equal to I lower star of, I can take star, well, it's the sum. And I L upper star, that's the inclusion from the L point, D. So what does this mean? This is just, it's a fixed point, so this is just a representation of the torus. Right? It's a representation of the torus. So this is living in the Chow groups of BT. But I have to multiply, I divide by the top Chern class of, well, the normal bundle of this point X in X, which is just the tangent bundle of X restricted up I upper star. Okay, and this just follows from the fact that when you push forward and pull back, it's multiplication with the top Chern class of the normal bundle, and the normal bundle is the tangent bundle. So that's the Bott residue. Right. Well, maybe this is the sum. Say it, and this guy here is living in, but now I have to invert something. I have to also invert these guys, right? So this is living in the chow group 0, or chow whatever of Z. Now I have to invert C and this product of these classes. So I've got to invert a bunch of things. I have to also, of course, invert that there. Now, I've inverted all this stuff, but I'm only the point is that as long as the points are really fixed points, this will be a non-trivial representation. Every time you have a fixed point, it means that in all the tangent directions, the group is acting non-trivially. So this thing will be non-zero. That's the point. So by inverting it, you're inverting things, but you're not losing the integral information. These arguments work more or less the same way. So more or less, the same thing works. For G equals N. Homology or G equals N. Okay, so the less comes from the following. The less is, so there's a warning, less might bring that can happen. It's unfortunate. Okay. Or so that's really less. That's really bad. This can happen. This can happen in the case of SL to the N. So slightly less. I don't know. So you might be inverting 0. This only happens for G equals N. This only happens in the following situation. So remember, N contains this GM. And let's say this guy here was the fixed points by GM, but then you have this extra guy sigma. And let's say this guy here is the XN. Then you essentially have just a one-dimensional or a sum of one-dimensional normal bundles, and we know that the Euler class of something one-dimensional is 0. So when you want to invert the tangent bundle restricted to here, the representation will have Euler class 0, and that's bad. Okay, so this won't happen if you assume that the sigma is just permuting the components of this guy here, which is what happens in most cases of interest. Okay, so except for that situation, but then there's a slightly less even problem with N. The things you're inverting, the classes you're inverting, even if they're non-zero, they may have even integer leading coefficients. So inverting an even number is also bad when you're talking about the Witt group, because except for the reals, the interesting information is usually two-torsion. But there are ways around this, which you have to work arithmetically to spread your problem out as much as possible over the integers, and then the Witt group is just the integers. So inverting a few things doesn't matter. Okay, good. So with that, I didn't really state a theorem, but I'm just saying more or less the same thing works. So in the remaining 5 minutes, let me give an amusing example. So the classical case of a torus action is on a projective space, where you just have the torus acting, the ith variable acts by multiplication on the ith coordinate. And then, of course, it's sometimes unpleasant to work with this big polynomial ring. You can reduce it down to a GM action, which also has the same vertices as fixed points, by just taking t multiplied by t to the a0 on x0, t to the a1 on x1. You take the a's to be widely separated, and then still the fixed points are just with vertices. So you can do the same thing with n. You do this with projective space, you get nice computation of, say, the Euler characteristic of projective spaces or Grassmannians by just counting number of subspaces that contain various lines. So it becomes a simple problem. Those are computations that are already known, so since I don't have much time, let me just ignore that. But let's take the n action on, let's take case of P4. It works in general on Pn, but where you have this element T inverse acts by, say, t to the a, x0, then t to the minus a, x1, e, 2, t to the minus b, 3, and then it leaves x4 alone. Let's assume that a is much bigger than b, which is much bigger than 0. And for reasons which I haven't gotten a chance to explain, let's assume that these are both odd integers. Yeah, that's the way it is. And then, of course, sigma acts by the obvious thing, just by the matrix it has to act by. Okay, so the picture is you have these two interesting lines, and you have the vertices E0, that's where the 1 is in the 0 spot, x0 spot, then you have E1. 1 is in the first spot, 0 is elsewhere, and you have 2, 3, and then somewhere out here you have this fixed point E4. So that's the picture. The torus action moves these things along, and the sigma reflects these guys here. And everything is fixed here. Okay, so that's how the action looks. And now what we're going to do is we're going to look at the question. We take x inside of P4, general cubic hypersurface, not quintic, sorry. Quintic. People, and this guy had a lot to do with the initial story of Gromov-Witten theory and string theory and all that, where these guys computed the number of twisted cubics lying on this thing, of cubic rational curves lying on this thing, and the physicists came up with one number, the algebraic geometers came up with another number, but then it turned out they were wrong. They made some mistake, and then they corrected it, and they both got the same number. So that's the history. So that was the algebraic geometry side. Maybe I just, yeah. So since I'm completely out of time, I'll just say won't say anything about this. Using the setup. So this was suggested by John. Yes, 3. I was getting the wrong order. So. Right. He suggested that I could look at this problem, and then this is so suggested by. So use this setup, and then you want to look at the sheaf essentially of forms on some subspace of the Hilbert scheme, parametrizing all the twisted cubics and their limits in the projective space. And essentially the answer that the Ellingwood-Stroma thing was to compute the top Chern class. 5, and this gives the number of cubics x, and what we do is this, they use the localization method with a torus action, and we use the same thing to compute the Euler class of this thing. And this gives whatever, gives a quadratic form, which lives in the degree of this thing, which lives in the big ring base field. And the answer that the answer, so this is so we already give the answer that this thing, this degree equal to 765. So just to say how you, just let me say one word, that when you do this, in this case, there are 6 fixed points. And they call, for example, you want to get a cubic curve, so you can take a cubic curve, which is this line, and this line, and this line. And when this line is fixed and the sigma switches these 2 lines, but the cubic curve itself remains the same, or you could take this one and this one. You could do the same thing using this line. That's 4 of them. And you can take this line doubled. In other words, you take the structure sheet modulo the square of the maximal ideal. That's also a cubic curve. And that gives you the 6 fixed points. And then you have to compute all the representation theory and do this, and you get some funny rational function at each point in A and B. And the miracle is when you add them up with the right signs, it adds up to a number. So, so it's funny. And that's the number. Just let me make sure. And of course, she did a lot of other calculations for many different situations. You can do this for, in general, you can do this for a hypersurface of degree D inside of Pn, as long as 3D plus 1 is equal to n. And you can do the same thing for a complete intersection of degrees Di, as long as the sum of these numbers is equal to 1. The answer, and she actually wrote a program that computes the answer. So just for fun, I'll remember time, but just for fun. It's always fun to see a table. And I got it wrong, of course. I see that. So, okay, that's it. Okay.